yesterday, I just do a quick revision, what we covered yesterday. I started with a bit of the background and telling you why I had a bit of interaction with the use of FEM in practice, and still doing it actually at the moment. So basically, that all culminated in the collapse of the Nickel Highway in 2004 in Singapore, and the subsequent committee of inquiry, which basically tells the engineer a lot of this gobbledygook about method A, method B, which a lot of them are probably none the wiser, So basically, that kind of sets the scene for a specialized course, and in the NUS, the specialized course that we have to train engineers in geotechnical engineering is the MSc Geotech. Okay. The important point is that if you want to be licensed as a specialist, geotechnical specialist, professional engineer in Singapore, you have to have a postgraduate degree. That's one of the requirements now. Postgraduate degree majoring in geotechnical engineering. So this is very important. So it's a fundamental requirement. So that is the first part there. The second thing is to talk a little bit about factor of safety. What is the problem? Really, the main problem is that the main use of finite element in practice is for people to come up with some numbers on ground movement and displacement. That really one of the main things. And also to give some prediction on the bending moment on the walls, that kind of thing. So these are kind of things that will need something more than the limit equilibrium method to do. So that is the reason why. Okay, so then we went on to elasticity, concepts of elasticity. The main thing about here is that first, there are 6 stress components you need. You need 6 stress components to completely define the state of stress at any point in 3-dimensional space. All right, and corresponding to the 6 stress components, you have 6 strain components. Okay, so these are the 6 strain components, and we then went on to define the stress-strain matrix. And I will just skip over some of these things. The stress-strain matrix is given by a 6x6 matrix, either relating the stress to the strain or the strain on the right-hand side to the stress. This is the typical form that we used. And you can also express it in this particular form. The main thing is that you need only 2 parameters. You need only 2 parameters to completely define the characteristics of a linear elastic isotropic material. The 2 parameters typically could be Young's modulus and Poisson's ratio. It could also be Young's modulus and shear modulus. And another common combination which is commonly used in finite element is the bulk modulus and the shear modulus. So this is the form. K represents the bulk modulus, G represents the shear modulus. So this is what we have. And then we went on to 2-dimensional problem. I don't want to spend time on this. Basically just to say that with plane strain analysis, the 6x6 become a 3x3 matrix. So this is one of the main things. And then we went into concept of effective stress. Talking about concept of effective stress. And this is the full set of the effective stress equation. The main thing is that water carries no shear stress. Water carries no shear stress. They only help to carry the normal stress. So in a sense, it helps to reduce the effective stress, but it doesn't do anything to the shear stress. Okay. In fact, in most cases, we usually do not talk about effective shear stress. We talk about just shear stress. Because effective and total is the same thing, one and the same thing. Okay. Then we talk about the drain and the undrained condition. Basically, just to define the drain and the undrained condition. The main point that I want to recall is that there are 2 quantities. 2 quantities. You control one quantity and the soil control the other quantity. In the drain situation, you control the pore pressure at the boundary. Fix it. But then the soil will control how much water flow in and out. You cannot control that. In the undrained situation, you control the flow at the boundary. In fact, you control no flow. You specify that there's no flow across the boundary. So water, you basically control the amount of water to 0, water flow to 0. But the soil will control the pore pressure inside. So you cannot control the pore pressure. Even the boundary pore pressure is not controlled. Okay? So in the undrained analysis, you typically do not need to set a pore pressure boundary condition. So this is the 2 ends of the strings that we were talking about yesterday. And then we went on to define the volumetric strain. And the main thing after that was looking at how finite element software would actually perform an analysis if you perform an effective stress analysis, because even an effective stress analysis is one in which you put in effective stress parameters, K dash G, that kind of thing. Okay, but how does the soil then get the total stress parameter, or how does the soil transform everything to total stress? The trick in the program that is being used in most programs is to add on a big number. This big number in this matrix is given by Kw over N. Kw is the bulk modulus of water, N is the porosity. So you don't have to exactly capture this bulk modulus of water, but all you need is a number that's much bigger than K dash. This number just needs to be much bigger, typically 1,000 times bigger than K dash, and you'll be reasonably accurate. So basically, what this does is to transform this particular stress strain matrix to one that actually describes a nearly incompressible material. All right, and so then this allows you to solve the effective stress analysis, and then we went on to describe the two ways that people can actually use to solve an undrained problem. A, by using undrained parameters, EU and nu U equals to 0.49. The other one is to use effective stress. The main advantage of using EU and nu U is that you really only need EU, because nu U is very close to 0.5, and you will just put a number of close to 0.5. But it has a disadvantage in the sense that it will not be able to extract the pore pressure and the effective stress for you. So you will not have any information on the pore pressure. All right. The second one is to use effective stress analysis using E dash, nu dash, or K dash, G dash. You need one more parameter. You need to know one more. You need two parameters instead of one parameter. But the advantage is you can actually have an idea of the effective stress and the pore water pressure. So you will be able to extract the result for the effective stress and the pore pressure for you. So basically, we then went into stress path, and that was the story of S and T and P and Q. Okay, I think I went through the whole set of stress path parameter. Essentially, S and T is very commonly used in practice, where it is also called P and Q. So when you see a graph of P and Q in practice, make sure you check what is the definition. And usually the definition is given together with the axis. Like yesterday, P equals to half of this plus this. Then you know it's actually S, because there's a half there, a factor of half. Okay, so basically this is the difference. And I mentioned S and T is used more often in practice, but P and Q is used more for constitutive models. So if you want to understand constitutive model, you really have not much of a choice but to know something about P and Q. Okay, and I want to, at this point, just make the important point, which I mentioned yesterday as well, and that is that regardless of whether you're using S and T and P and Q, you think of it this way: S and P is a characterization of the normal stress. It's some measure of the normal stress. All right. So S dash is some measure of the effective stress. P dash is some measure of the effective stress, except that they take different components into account. How you count that thing, what you put into the basket to count. Now, T and Q are actually measures of the shear stress. Okay, T is called the deviatoric stress because the Americans call it deviatoric stress, and it was started by MIT. So that it has it is kind of sacred in America. All right. So whereas Q is started in the UK, so the British call it deviator stress. When you do a triaxial test, when you plot stress strain curve, the stress you usually plot is the deviator stress, the diameter of the Mohr circle, and the triaxial test. So that is the deviator stress. Now, they are both measures of the shear stress. One is the diameter of the Mohr circle, one is the radius of the Mohr circle, and it really is gives you a sense of the largest shear stress in the soil element. Okay, so in a sense, like I told you, P and S are the good guy, P dash and S dash are the good guys, and Q and T are the bad guys. So it's really nothing more than a plot of good guy versus bad guy. And you have been doing it in undergraduate soil mechanics when you plot sigma versus tau, and then you got a Mohr Coulomb failure envelope with a Mohr circle. You're really plotting good guy versus bad guy. Because sigma is a good guy, sigma dash is the good guy, tau is the bad guy. So it really is the same kind of thing. So if you think of it as an extension of that kind of concept, it's actually quite easy to accept that. Quite easy to accept. Okay? So essentially, I just went through a few stress paths for you, and then I then went through, this is Q, looking at Q, and then talking about how you can use P and Q to understand Skempton's pore pressure parameter. That was the last part. Okay, how you can actually show in a very simple way that, this is what it is. In a very simple way that B should be 1 for saturated soil. How you can easily show that B equals 1 for an undrained test on a saturated soil. And how you can show that A must be equals to 1/3 for a linear elastic material. Alright, and this has all to do with the fact that on the PQ plot, okay, if you do an undrained test on a linear elastic material, as long as A equals to 1/3, or as long as the material is elastic, okay, as long as the material is elastic, the stress path, the effective stress path will be a vertical straight line. You don't need to know anything about the total stress path. Whatever the total stress path is, the effective stress path will be a vertical straight line for an elastic material. Alright. So if you have a quiz and they said, please draw the effective stress path for this elastic material subjected to this total stress path, you don't even have to think one straight line. Okay? Because it's independent of because the question, the main point about is related to the condition of undrained analysis. And the condition of undrained analysis is that there is no volumetric change. No volumetric strain. No increment, no change in volumetric strain. And as a result, because volumetric strain increment is directly related to change in P dash. If there's no volumetric strain increment, that is the basic thing about undrained condition. No volumetric strain increment, no change in volumetric strain, there cannot be a change in P dash. Simple. You don't have to worry about what the total stress path is. I can give you 101 different total stress path. There's only one effective stress path. That's vertical straight line. Is that alright? Okay, so that brought us to the end of yesterday's proceeding. So I just want to wrap up yesterday's proceeding by showing you something very quickly, some test result. And I'm sure you already, in your undergraduate, I'm sure your lecturer or teacher would have told you, soil is a non-linear material, or soil is an elastoplastic, is a plastic material. I'm sure at some point of time, you will have that being kind of told to you. So I don't think you need much convincing that soil is not a sponge. Soil is not an elastic material, it's not a piece of rubber, that kind of thing. It is quite different, you know. So basically, I just thought I would just say something to reinforce it for you, you know. Basically, I show you 4 tests. In this classic test by Henkel. Henkel is the co-author of the book by Bishop and Henkel on triaxial testing. So he's a big guru in triaxial testing. And essentially, he has done 4 tests. Test 1 and 3 is normally consolidated. You can see it's on the virgin compression line. Test 2 and 4 are on a swelling line far up there. Same, pretty similar water content, pretty similar void ratio, you know, but this is heavily over consolidated. And test 1 and test 1 and 3, one of them is drained, one of them is undrained. Similarly for test 2 and 4, one is drained, one is undrained. Okay, so basically if you look at it, test 1 is a drain test, and you can see the result of the drain test quite clearly. The stress strain curve is non-linear, quite clearly. All right. I won't say too much about the volumetric strain. The volumetric strain is also non-linear as a function of the axial strain. Similarly, for the undrained test, you can see that the deviator, the stress strain curve, this is what you typically plot for triaxial test. When you plot stress on this is really the diameter of the Morse circle. It is also the deviator stress. Okay, and you plot it against axial strain, and it's obviously non-linear. So we don't have to say too much about this. And similarly, for the heavily over-consolidated test, for the strain test, you can see that you can just make out the peak strength, okay, at the point of failure, and then it comes down after peak, okay. And similarly for the undrained test, you can also see that it is pretty non-linear. So basically, quite evidently, the linear elastic model is insufficient for a lot of soil. I won't say it is insufficient for all sorts. But if you hit a piece of rock, I think you have good reason to say, I think it is going to remain elastic, because for the stress level that you apply onto the soil, or that the soil can apply to the rock, I think the rock will be, if it's a fresh piece of rock, I think it will be fairly elastic, you know. And so basically, I think certain instance where you can justifiably use an elastic material, if it is a very, very, is a good rock material, or very hard soil even, but usually, even for very hard soil, we usually play it a bit safe by using some kind of more Coulomb. Although there's some issues about how you're going to fix the parameter for that, even for the more Coulomb, if you want to use it. But essentially, we can discuss a bit more on this later on. But, okay, so this brought us to the end of the elasticity part, okay? And I now want to move on to the next part. So this part, I call it perfect plasticity and more Coulomb. And really the focus is on more Coulomb, and it is to address some of the background issues that I covered yesterday early morning. Now, it has long been observed that in fact, this truly linearly elastic material is really only elastic within some well-defined limit. There's never one material where you can stretch it to infinity and then the guy is still elastic. It's very hard. I mean, somewhere along the line, the guy is going to break up. It's either going to break up, it's going to yield, it's going to do all kind of things. Anyway, it's going to fail. All right. So basically, and some material are never truly elastic. Even rubber, for example, rubber is never truly elastic. So basically, what you can see here is you can see a variety of material from various things. I mean, this is a piece of a mild steel. You know, it is elastic up to here, and then it does all kind of funny things. You know, there's an upper U point, lower U point, and then it went into post U, and then, but it's still going up. It's still going up. All right, and then you get a breakup over here, and then you got a cemented tungsten carbide over here, which is linear elastic up to this point, and suddenly it just completely fractured. It is a brittle material. Okay. Now, the important thing is that I want to highlight, we will not be covering the behavior of brittle material. The framework that I gave to you for plasticity does not cover brittle material. Okay, brittle material fail by tensile most of the time, tensile fracture. So tensile fracture is more related to fracture mechanics. Okay, I'm not saying that you will not hit that kind of scenario in practice. Sometimes when you have very, very cemented soil, we found that for example, if you cement treat the soft soil, you know, when you deep mix the soft soil with cement, and then you start to make a tunnel through that material, there is a chance that you may get a crack on the crown of the treated soil. All right. So we need to be, and engineers, the one thing about I always noted is that a lot of codes, structural codes and all that, they are very, very careful about tensile failure. They really try to avoid tensile failure. So usually I will tell people, if there's a possibility of tensile failure and you can avoid it, please avoid it. You know, because it's a very brittle, very catastrophic situation. You cannot really control the thing. You know, so basically this is what happened. And same thing with the plaster of Paris. Plaster of Paris, when you pull the plaster of Paris up to a point, it just cracks up and go. And you can see that there's hardly any non-linear, but up to a point it just collapses. It just break up. Okay, and then you have soft rubber. The soft rubber is elastic up to this point, and it just break up. But in fact, even within the elastic range, it is non-linear. It is non-linear. So essentially, this is the situation. Okay, so these are some real material behavior, and this is another one. Copper wire under tension. You draw the copper wire out, and you can see that initially there's a U point over here. This U point over here. All right, and if you kind of expand this region out a bit more, you will see it looking a bit like that. Okay, and you can see this is the ultimate tensile strength, and then it just fractured. So this is typically just to show you that no material is infinitely elastic. No material is infinitely elastic. So whether you like it or not, if your stress level is high enough, there will be some change of regime coming up, what we call a change of regime. And a change of regime could be a catastrophic failure, it could be some kind of non-linear behavior, or it could be the onset of plasticity. Okay? Now, The class of material behavior that we are talking about in here is a class of material that beyond a certain stress level, if you look at this, copper wire for instance, if you load up the copper wire to here and you unload, it pretty much will come back here. But beyond here, say you come up to here, when you unload, it will come down here. It will come down here. It will not come back along here. This is the essence of plasticity. The material will flow, but when you unload it, it will not resume its original configuration. There will be a certain amount of irrecoverable deformation. Irrecoverable deformation. And the presence of irrecoverable deformation is a hallmark of plasticity. In fact, that is a thing that is used to define plasticity. Now, I think for you all, I don't think I need to convince. I don't think you need much convincing that soil is elastoplastic. But when I teach fundamental basic soil mechanics course, because these lads or second year kids in the university, they are not so conversant with this. So I usually give them some example and I said, if you want to show how soil is plastic, all you need to do is to walk on a muddy field or walk on a beach. The very fact that you leave a footprint tells you that that material is plastic. If you try walking on a piece of sponge, you will leave no footprint because the moment you take your feet off, it just bounces back. That is the difference between a sponge and soil. Alright? That is the difference. And the soil basically has this thing that when you step on it, soft mud, clay or whatever, or soft sand, it will actually go it will actually leave a print. That is irrecoverable deformation in the simplest form. Okay? So basically that is a everyday demonstration. You walk on a muddy field, is an everyday demonstration of why we say soil is elastoplastic. Okay? So this is the kind of material. We are not going to cover things like tensile failure and all the rest of it. This is strictly that class of material. And this class of material is very prevalent for soft soil. Okay? And my understanding is that in India, in your country, there's no shortage of soft soil. Am I correct? No shortage of soft soil, especially around the coastal area. I think Bombay, you got plenty of it, right? Right. Somewhere around the, yeah, because I've read some papers on this, and basically, you got some very famous soil types around in your country. So essentially, yes, this will be the kind of material that we are dealing with. Okay, so the main thing is that there will be irrecoverable changes and the material will not return to its original configuration when you unload that material. And so that is the difference between elasticity and plasticity. Okay? Now, how do we need to regard the onset of plasticity? How do we need to regard the onset of plasticity? We need to regard it as essentially as a change of state or change of regime of material behavior. And because of that, you need some new rules to define. You need some new rules to define plastic behavior. Okay? The existing rule that we have learned yesterday, which is the generalized Hooke's law and all those stress and strain proportionality, that works very well with elastic material. But it doesn't work with plastic material. So you need new rules, and the new rules, at first sight, is actually less intuitive. Okay, let's take a look at this example of plastic behavior. There's a copper wire being drawn, and you can see that this is the point A. Is the point where you unload it, and it comes back down, and you can see that it unloads down to point B1. And B1 is not A. So basically, there is a certain amount of irrecoverable extension of the wire. And then you reload it again. You actually follow back this point until it hits the U point, the new U point. You see the copper wire is a material where the U point is increasing all the time with strain. Alright? This is what you call a hardening material, strain hardening. So basically the U point will increase until you reach A2 when you start to unload, and then it comes down to B2. So it will not go back to B1, it will not go back to A, it will go back to B2. So this is the essence of plasticity. Okay? Now, there are few basic ingredients that you need to use to describe a plasticity model. The first one is what we call a U criterion, and the U criterion is probably the thing about plasticity that you would have come across, that would have you would have interacted with the most, that will be most obvious to you. The U criterion, for example, the Moore Coulomb failure envelope is used as a U criterion in the Moore Coulomb model. That's exactly what is done. Okay. Now, what is the U criterion? You realize that the plastic behavior does not start from zero stress state. Typically, it doesn't. It doesn't. All right. It needs a certain stress level to, in a sense, activate that plasticity. Activate that plasticity. So you need to be able to say, okay, at which point, at which stress level or above which stress level do I get plasticity? You know what I mean? Above which stress level would I start to get plasticity? Now that is a criterion. Now that is fine if you just have a wire and you're drawing it and you say, I take the force divided by the cross-sectional area, I got the axial stress, and I say, above this axial stress, I will get irrecoverable deformation. Now that is fine. That is for a one-dimensional problem of a copper wire. But if I give you a three-dimensional problem where you have all kinds of stresses, 6 stress components, 3 normal stress, 3 shear stress acting, then you suddenly realize, I really probably need more than 1 stresses to actually define the criterion. But whatever it is just a limit. A criterion is nothing more than a limit, a combination of stress or a function of stresses above which you are going to get plastic behavior. That's all it is. Okay? So we are going to use the Moore Coulomb as a good example to show us what is the U criterion. What is an example, a good example of a U criterion. So basically in a more complex stress situation, your U criterion may be more complicated. Okay? Because a single stress component or single stress parameter is often not enough to characterize the condition governing yielding. Okay? So you will need to define as a combination of stress or combination of stress parameters. Okay? So basically this is how typically a U criterion is defined. And so I have just sketched out what is a possible example of a U criterion. And in this case, I've defined a U criterion in terms of the stress path parameter, and you will know that this P dash is actually a combination of 3 normal stresses. Half of 1/3 of sigma 1 plus sigma 2 plus sigma, or 1/3 of sigma x plus sigma y plus sigma z. So, and Q is some complex square root combination. So what you're looking at is really a function of relating all the stress component. And the idea is that if you are below this line, which is the U envelope, you are elastic. If you are above this line, then you are plastic. Alright? But in fact, you cannot go above that in a perfect plasticity because this line tells you this is the limit, you cannot stop. You cannot go beyond that. You cannot. So this region here is inaccessible and this is the plastic region. This is the plastic region. Okay? So this is the plastic. Now, I deliberately draw this thing in this particular form because it looks something like a Moore Coulomb failure envelope. And this is essentially how a Moore Coulomb model that uses the Moore Coulomb failure envelope as a U criterion. So basically, you can see this is the good guy and that's the bad guy. If you have more good guy, you can take on more bad guy before the thing starts yielding. Right? If you have less good guy, then you take on less bad guy before you start yielding. So this is the good guy and versus the bad guy scenario. So basically, a U criterion is some combination. What is the combination of good guy I need to deal with this combination of bad guy? You know what I mean? Okay? So this is essentially how it looks like. And the common way of expressing a U function is like F as a function of stress parameter equal to 0. Okay? So typically the way the finite element program works is that it will express it something like that. But if F turns out to be negative, that means it's elastic. If it turns out to be 0 or greater than 0, it is plastic. Okay? So this is the way it actually works. Alright? And quite often, you find that people prefer to express the function F, the U function, in terms of stress invariant because it's much easier. P and Q are stress invariant. To express it in stress invariant is much easier to deal with than to express it in terms of stress components. Okay? So, now, I just want to emphasize that, in fact, even in an plastic situation, even after plasticity has occurred, there is still elasticity. Elasticity does not vanish the moment you get plasticity. It's there. It is there all the time. Alright? Except, let me just show you why I say it is there all the time. If you look at a copper wire thing, if you unload from here, say here, A, when you come back, if you look at this line carefully, it's not exactly vertical. There's a gradient. There's a gradient. That gradient tells you that when you unload, there's a small rebound. That rebound is elastic. Elastic rebound. But in general, the plastic strain is much higher than the elastic strain. And so it kind of overpowered that guy. But the elastic strain is still there. Is that alright? So basically, in an elastic situation, in a true fully elastic, until the U stress or U condition is reached, you only have this green band, which is the elastic behavior. The moment you pass this U condition or U stress, then both the red band signifying plastic behavior and the green band signifying elastic behavior will be there at the same time. So they will coexist. They will coexist. Okay? So the U criterion is just, the U condition is just a condition saying that plasticity will start from here. It is not a condition that says elasticity will vanish. Is that okay? Okay, the first criterion tells you when will you get plasticity? That is, at what point will you start to get plastic behavior? Then the next question must be, after you get plastic behavior, how does the material behave? Do you still follow the Hooke's law? You know what I mean? But in fact, I already told you that the Hooke's law doesn't work, so it doesn't follow the Hooke's law. Now, it turns out that for historical reason, the way that the early people who work on early plasticity chose to describe plastic behavior is through what they call a flow rule. A flow rule. Now, this thing may appear to be a little bit counterintuitive or rather, abstract to you. But essentially, what a lot of people, okay, I will try to explain it from different directions. The first way to explain it is this. When the early workers of plasticity study a material, the first people who study plasticity are the metal working people because they need to do metal forming. And when you do metal forming, the guy has got to go plastic. Otherwise, when you press something into a new shape, you let go, the guy come back. It doesn't retain the new shape. So if you want to form, when you want to extrude materials, metal with different shapes, you got to force it into a plastic state. And that is when they started first working with plasticity. And what they found was that when the material go plastic, it appeared to flow like a fluid. It appeared to flow. That's why the word flow, plastic flow. It appeared to flow like a fluid. And so they wanted to see if a method for describing fluid flow is applicable to plastic material. Now, from the soil mechanics point of view, there is a very simple analogy. When you are doing your seepage, your third year seepage analysis, there's something called a flow net. And a flow net consists of two sets of lines. One is the equipotential, which is lines of equal heads. The other one is actually the streamlines, which tells you the direction of the flow. And there's a very important condition. Supposing these are the equipotential, and these are the streamlines going out. Let's say the arrow going this way. These are always at right angle. Correct or not? These are always at right angle. So basically, the direction of the flow is always at right angle to the equipotential. So the plasticity people say, can we use a similar way to describe plastic flow by prescribing a potential function? A potential function in terms of stress path parameter or in terms of stresses. A potential function to which the material must flow at right angle to. Alright? So that's why they come up with this thing called plastic potential. The idea of plastic potential is actually essentially an imaginary line in the plastic space whereby the material is using that to direct its flow like a streamline. Okay? Now, I figured that this is probably a little bit still abstract to you because, honestly, how do you relate a steel that is undergoing flow to water flowing through the soil. Not so straightforward, right? Okay, this is the example of what happens. So you can actually, what they say is this: a flow rule governs the way in which the material deforms. And the most common way is to use plastic potentials. That means to draw an imaginary set of lines in what we call PQ space or some form of stress space. When I use the word stress space, just to define, when I use the word stress space, it is usually a plot of stress versus stress. Typically, sigma versus tau, or tau versus sigma, Q versus P, S, T versus S. That kind of space is called stress space. It's nothing more than the plot of ST, PQ, or sigma tau kind of plot. So we call this stress space. And basically the idea is that you can the hypothesis is that you can actually prescribe a set of lines which are called plastic potential in this particular form along this particular space, where you can take arrows at right angle to normals to this line that describe the direction of plastic flow. And the direction of plastic flow is described in terms of strain increment, shear strain increment, plastic shear strain increment, and plastic volumetric strain increment. Now, this is typically the framework by which people prescribe plastic flow. Now, at this point of time, a lot of things are still unknown. For example, what is this shear strain? Because this is not the normal shear strain. I will define the shear strain when I come to more Coulomb in a short while, later on today. But volumetric strain, you probably know. The superscript P there is for plastic behavior. Okay? So this is, in a sense, how the framework of the flow rule looks like. Now, it may still be a little bit counterintuitive. So basically, I will skip this portion first. I'll come to it later on. There is basically two types. One is called associated flow. The other one is non-associated. But we'll skip this part first. But the main thing now is that I don't know how many of you have done plastic collapse of bottle frames. Have you? How many of you are familiar with plastic collapse? Are you all familiar with plastic collapse? You didn't? Okay. Basically, in plastic design, you got a frame. The idea is that when you load the frame up to a certain point, you will get some what we call plastic hinges, the point at which the bending moment has reached the critical limit, and then the guy starts to rotate like a hinge under a constant moment. This is called plastic collapse. And the people who done a lot of this work, in fact, John Baker was the one who instrumental in doing this. Now, I want to use this. If you don't understand this, never mind, because we are going to use more Coulomb as an example later on. But if you understand plastic collapse of frame, this may interest you to know that it actually follows the idea of a flow. It actually follows the idea of a flow. And I won't go through the mathematics, which I think the algebra is quite... I didn't show any of the algebra here, in fact. I've shown a frame here, a simple frame with 3 modes of collapse. If this is the first mode of collapse, where your horizontal load is much larger than the vertical load. So basically, you push the frame and the guy just fall over. All right? That is what I would call a sway mode. It's just sway over, the sway mechanism. And the sway mechanism is governed by the limiting horizontal load. The limiting horizontal load given by this thing. All right? This is the limiting horizontal envelope. And then you would have the opposite, the other mechanism, the other extreme, which is called a beam mechanism. This load is very light, the H is very light, but very small, but V, the vertical load, is very heavy. So if the vertical load is very heavy, the horizontal load is not enough to cause any plasticity. The vertical load can cause the plasticity. What happens? You got a thing moving downwards like a beam, right? Collapsing like a beam. And that is totally dependent on the magnitude of the vertical load, and therefore the failure envelope is this particular straight line. This particular straight line, the horizontal straight line. And in between, you will have a mechanism that is a combined mechanism that is governed by this failure envelope. This failure envelope. Okay? Now, so basically, if you look at this, the intersection, the area underneath these 3 failure envelope is essentially your working area of your working envelope of your frame. Right? Now, let us think about this for a moment. I'm not going to derive the working envelope mathematically. But what I want to say is this. Supposing you got a situation where the load is just short of H, just short of the loading situation is just somewhere around here, which is to say the horizontal load is almost sufficient to cause collapse. But the vertical load is very light, nothing. Alright? So let us take an example. You got a load here, load combination. A load combination. Let us take, for example, you got a load, just put some numbers to it. H equals to 1000 kilonewton. And V is equals to 1 kilonewton. So V is very light. It's not enough to cause you any. It's like mosquito bite, on the thing. All right. H is almost there. Almost there. Now, supposing you come along, and we say we just add an increment in H of about 0.1 kilonewton. All right. Whereas for V, I add a lot more. I add another 10 kilonewton. Okay? The question is, which mechanism are you likely to set off? The first mechanism, right? The thing that you're going to go like that. Because this is the last straw that broke the camel's back. This is not anywhere near to breaking the camel's back. So the guy is going to go this way. So if you look at the way the guy is going to go, the deformation mechanism tells you that there is only going to be a horizontal movement and no vertical movement. And so when you draw the deformation arrow, the deformation vector will show you that you only got horizontal deformation and no vertical deformation. The important point is this. In plastic deformation, the thing that matters is not your stress, not your load increment or stress increment. In elasticity, you know that deformation increment is proportional to your load increment, right? That is the Hooke's law. But now you got a funny situation. This 0.1 kilonewton is critical. This 10 kilonewton is non-critical. So basically what it's telling you, this is more important. This is more important because this is bringing you almost to the point of collapse. You know what I mean? So in plastic behavior, the important thing is actually not so much the stress increment in deciding which direction to move, but the existing stress level. And I always like to draw a picture of two camels. Okay? I don't draw a camel very well, so you think of it, a camel looks like that. So this is a camel, and this camel you put on a small amount of load here, and then you come along and you decide I want to put another bigger amount. Okay, no problem, the camel will take it. Now, the second camel you come along, I don't know how to repeat this camel, but I guess 2 humps will do. Okay? And then you already put in a huge amount of load. The guy is almost collapsing. And then you say, perhaps I add one more straw in here. Boom. So the one straw is more deadly than this big increment. You get what I mean? No? That is the essence of plasticity. What sets off that plastic mechanism? Similarly, you can look through the rest. The other 2 arrows, you can see that they activated the other 2 mechanisms, and as a result, basically, the interesting thing to note is this: the deformation vector is always perpendicular to the failure envelope. Do you see that? So in a sense, this guy is behaving like a potential. This thing is behaving like a potential, and this is the direction the guy is going to move. And so at this point, this deformation is taking a cue. It's taking a cue from this particular segment of the line. It is at right angle to that line. Okay? At this particular point, this guy is taking a cue from this line and is at right angle to this line. At this point, this guy is taking a cue from this line and is at right angle to that line. So this is the notion. This, I hope, gives you a preliminary illustration of what we call plastic potential. So the failure envelope there is in effect behaving like a plastic potential. That is how the early people, you see, the thing is that in the early workers of plasticity, there's a few places in the world that are sort of like, that were famous. One of them is Brown's University, where the 2 kingpin were Daniel Drucker and William Prager, the upper and lower bound plasticity, lower bound. Then on the other side, dealing with the frames, you've got the Cambridge people, which is Baker, Michael Horn, and various people who are dealing with this thing. And there is a lot of cross-fertilization of ideas. And then this thing gets cross-fertilized across. So basically, that's how the notion of plastic potential come into being. But essentially, what you're saying is that the material is taking a cue from the failure envelope or the U envelope or the U criterion as a way to decide where it should go. This is basically what it is. Now, I always, and there's an analogy that I come up with to convince people, is that this is a kind of there is a bit of political overtone to it. So I hope some of you who are more politically minded will not mind. But essentially, it's a bit like election, I don't know how the Indian system of election goes, but it's a first past the post, right? In the sense that, okay, let's say you got a district, all right? You are standing for election, he's standing for election, you're standing. Then how will you decide who gets elected? The guy who gets the most vote, right? So even if he win by one vote, he's going to get elected. It's called first past the post. The Italian has a different system. It's called proportional representation. If you got 55% of the vote, that 55% of the people in the district vote for your party got 55% of the seat. If 45% vote for you, then for your party, then 45% of the seat goes to you. That is what we call proportional representation. But this is not the way it works down here, right? And in Singapore, we also use the first part. That's the British legacy. You win the particular location by one vote, you win the whole thing. Winner takes all. All right? Same thing over here. So basically, the proportional system is like Hooke's law. All right? Our system is like plastic. All right? So basically, whichever mechanism is first triggered controls the situation. You get what I mean? So basically, so the plastic situation is actually not so alien. No? In politics, they use it all the time. All right? They use it all the time. So basically, this is an illustration of plastic potential. And the flow rule is going to become more real when we deal with the more Coulomb, because then we will see there's a quantity called angle of dilation. Now, those of you who have used Plaxis or some kind of FEM program on more Coulomb, have you come across this thing called angle of dilation? And Plaxis would typically by default set it to something like 0, I think. Have you ever questioned, what is this animal? What does it do? What if I set it to non-zero? That is the purpose of your assignment. What if I set it to non-zero? How will it affect the behavior of the material? You know what I mean? So this is, the angle of dilation is the more Coulomb's way of describing the plastic potential, essentially. So I will actually talk and go into detail in the later part of this part of the notes, because that is essentially an important part of the more Coulomb that you need to know in order to fully utilize it, and to fully understand the limitation of the more Coulomb model. Is that okay? So basically, we just leave it, the flow rule at this junction like this for a moment. I won't go through the whole thing, but essentially we'll come back to it in future. Okay. Basically, we'll move on a little bit because we're still talking about generally in general terms plasticity. This is just to illustrate to you that elastic strain is still present, but I think I've already done it with that better drawing of the copper bar, so I don't think I want to go through this whole thing. Okay. And you can see that copper wire there again. Okay. Now, I just thought maybe I digress a little bit. And just now I told you that the simplest way of showing people that soil is elastoplastic is to just use your footprint. All right. But there are other ways of doing it. You will still remember in your one-dimensional consolidation, you plot the E log P curve. You know that? All right. And you got the recompression line, and then the virgin compression line, and then the swelling line, and then the recompression line, and so on. Okay, let us take this opportunity to revise a little bit on that. And this is not a very good drawing. I couldn't use the word software very well, so the thing come out a bit crummy. So basically, RL1 is recompression line at the start. Supposing you got a sample starting here. You load it, you get recompression line, you follow the recompression line. If you unload along this recompression line, you will come back along here. Correct? This is the rule of the thing. Then after you pass this point, which is called the pre-consolidation pressure, the guy moves down the virgin compression line. Am I correct? It moves down the virgin compression line. Now, if you want to unload at this point, it will not come back here. Am I correct? It will not come back here. It will come back along here. And then when you reload from here, you'll come back here, and then you go up along the virgin compression line, and then when you unload from here, it will not come back along here. So this is a one-way street. You can't go back this way. All right? Similarly, when you unload here, you come down here, and you recompress, you almost follow the same thing going up. Are you familiar with this? Okay. Now, if you compare this graph with this graph, don't they look almost similar? You see, this horizontal axis is a measure of the deformation or strain. The vertical axis is a measure of the force or the stress. All right. If you look at it, the horizontal axis is void ratio, and void ratio is a measure of the volumetric strain. The vertical axis is either the mean effective stress or the vertical effective stress over burden stress. That is a measure of the stress. This, you see, I have plotted the E log P curve. Instead of going up, plotting the E on the y-axis, instead of plotting it this way, I turn this thing this way. You notice that I've turned it this way. Because you see, the soil mechanician somehow has a funny habit of plotting, whereas the mechanician plot stress-strain curve. In this case, we are plotting the E log P curve is actually a strain-stress curve. Somehow we got this funny habit of plotting the strain against the stress rather than the stress against the strain. So what I have done is I just sort of turn it back up this way. So soil mechanics has a funny history of development, and a lot of people in the mechanics field don't have a good opinion of soil mechanicians' mechanics. Okay, there was a professor, Ken Johnson, in metal plasticity in Cambridge, who used to tell people that soil mechanics is nothing but soil, and there's hardly any mechanics there. Okay, so that is his way of saying that these guys don't understand mechanics. He's not entirely wrong, although I take offense to it, but he's not entirely wrong. So basically, this is the situation. So what I've done is I turned the whole thing around. So the P-axis is now on facing vertical. The E-axis is now horizontal. So now it starts to look like a stress-strain curve. And when you look at it, don't they look rather similar? These two, the copper one. And so basically, it tells you that, in fact, if you think of it, the recompression line are the elastic regions. Correct? The virgin compression line is the plastic region, the elastoplastic region. And where is the U point? The pre-consolidation pressure. That is plasticity. So basically, the way you can regard consolidation curves is, this is the point where the guy goes plastic, where you can suffer irrecoverable volumetric strain. Okay, so this is a one way of looking at soil behavior in an elastoplastic fashion. That's why we often say soil is elastoplastic in nature. Okay. So basically, in the plastic regime, just to emphasize, the total strain increment is the sum of elastic and plastic. And the reason is because when you look at it this way, at this point you only get elastics in this region, the elastic region, you only get elastic strain. But the moment you pass the U condition, then the plastic strain starts to come in, and the total strain is the sum of this plus this. Right? You look at a copper wire, it's the same thing. Alright? Let's take a big one, right at the top. When you unload this, you look at this line, there's a bit of a rebound. So there's a small amount of elastic rebound at B5. From A5 to A5 to B5, there's a small amount of elastic rebound. But the big one is obviously this one. And the total is this plus the small amount here. Am I correct? So the idea is that total strain is equals to the sum of the elastic and the plastic component. Is that alright? Okay. Okay, the last component is what we call a hardening rule. The hardening rule will not kick in to this discussion. It will come in the chem clay, because I'll use the chem clay as a vehicle to as an example of a strain hardening material, And at that point, you will see why how the hardening rule comes to be used. Because many material, such as steel and copper, basically you just look at the copper wire, the yield stress is increasing all the time as you load it. So there must be a way of saying that how describing how the yield stress is going to increase with strain. That is what we call a hardening rule. Okay, so that's a third ingredient of plasticity. Okay, I have finished the general discussion of plasticity. Maybe we'll take a few minutes break here so that you can recap and ask me any question you have before we move into the more column. Yes. Okay, that depends on a lot on the yield condition of the rock, the criterion that governs the yielding of the rock. Say you got a rock sample. Let's take a simple example. I just sketch a simple thing here of a cube of rock. Let's say we take a simple example. Whether it is soil or rock, we're just talking about a plastic material. Okay, so basically, let's say you take a simple example of a soil, cylinder of soil. You load it first isotropically. All right, you load it isotropically. And so you're not going to fail it because it's isotropic. Okay, and then and then you start to unload. Let's say, for example, you unload it by reducing this lateral stress on the side, reducing the confining pressure, but keeping this guy the same. What do you think will happen? There may be a small amount of elasticity, but in fact, what you are doing is to induce shear stress, deviator stress, because sigma 1 minus sigma 3 starts to increase. And so as a result, what happens is that if you reduce it too much, the whole thing will just squash. The whole thing will just squash underneath. And that actually that's why I say that it depends on how your yield condition goes. In this particular case, in soil or I suppose in the plastic material you're talking about, shear stress is featured very strongly in the yield condition. And when you unload things from one face, even if you just keep this the same, supposing you keep this the same and you unload this guy, there is a chance that if you unload it too much and you keep squeezing it, this guy is going to come out like a toothpaste. It's going to come out like a toothpaste. So basically, what it tells you is that, in fact, this is an example of how the shear stress. So you can be unloading this face, and you may think, it's going elastic. But actually, there may be an elastic region, but it's going to be very small. And in fact, then, your shear stress is increasing, the deviator stress is increasing. So as a result, the whole thing is going to come out deforming plastically due to the strain, because it is actually driven by shear stress. I don't know if that answers your question, or you have another. Okay, so basically you are looking at, say let's take a simple isotropic unloading, loading first, then unloading, and then reloading, all round. Isotropically, all three loading, then unloading, all three unloading direction. Okay, basically you unload, there may be some yielding, and then you reload, there will be some elasticity. You will go back elastic because you are reducing the deviator stress. So you come back elastic. So you will come back to elastic. In fact, the most stable point is when all these stress components are nearly equal. That's an isotropic condition, and that is when it's the most stable condition. So the most stable condition is, so when you as you start to unload it, to load it back again, back towards an isotropic condition, you generally will get elastic behavior coming in. And then you will keep going on. You keep loading past this particular stress level. You keep loading. It will still be elastic, but beyond a certain point, it will go outside way. It will go outside because it's gone plastic the other direction. It's gone plastic the other direction. So in one case, it's squeezing out like a toothpaste. In the other case, it's washing out this way. So in between, you get an elastic regime. So you are fluctuating between two plastic regimes, two yield conditions. Okay. Sorry? Total strain is, sorry? The total strain, does it remain the same? Not necessarily. The total strain of this thing, you're saying that whether the total volumetric strain or shear strain remain the same. Is that what you're saying? Asking? Okay, the volumetric strain is only guided by one thing, and that is the P. So you have to take the average stress of the three normal stress, and it will change based on that particular thing. So there's no requirement that the strain must be the same. Okay, even if it is elastic, even when you start loading it back and you get elastic behavior, there's still elastic strain. You get elastic rebound. There's still a certain amount of elastic strain. So therefore, there's no, I don't think it is likely that you will get absolutely zero strain. You will get some strain. It's a question of whether you get plastic strain. You will probably in the interim region get no plastic strain. Correct. Yeah. The total strain in, yeah, so basically, okay, you reload it back, right? As you start to reload it back, obviously you will get, at that point, at the start, you will get no plastic strain because it's coming back to isotropic, there's no plastic strain, but you will get some elastic strain coming down. So you will keep loading it until you get past, until this guy becomes bigger, this stress becomes bigger than this stress. And you can continue to keep loading it. Up to a certain point, the plastic strain will kick in the opposite direction. You can. Because the plastic potential has a plastic potential function. But usually if you're dealing with something simple like a more Coulomb, you don't need to go to that plastic potential function. But later on, when I go into more Coulomb, I will give you an example of what the plastic potential function looks like. Because it's actually quite simple. It's a series of lines, and it's defined by a certain class of function. But of course, certain parameter will be changing because you do not just have one line, you actually have a whole series of lines. So in a sense, that value will be changing. That plastic potential will be changing. So in fact, yes, it can be described in that way, except that usually, in terms of plasticity, the way we look at plastic potential is we don't look at it as if it is an we don't look at it as if it's a hydraulic head. That's what we don't look at it like that. It is actually a function, a combination of stresses and things that come to a certain constant. And that constant can change. And that is, so along a certain line, that constant is the same. Along another line, that constant will be different. So that, yeah, you can describe it in that sense. That is describable. Okay, but it's not so, I guess I do not think of it that way. There are people who solve this problem mathematically, they think of it. But I usually think of it in a more graphical sense because I think of myself as an engineer. And I look at it, I think it's easier to accept things when you're able to visualize things rather than to kind of think of it strictly in a mathematical sense. And then, as engineers, I think we like to visualize rather than to try to work out the mathematics, And even when we work out the mathematics, I like to think that I have a mental picture of what that mathematics is going to lead me to before we do the mathematics, where we're going to end up in that sense. So I like to visualize it as a set of lines rather than a function, But you can express it as a function. That is doable and perfectly acceptable. I think there's no reason why not. Okay. Yes, this point. The pre-consolidation pressure. Yes. Okay, you're saying that, say you start at this point, and then you go up here, right? Oh, this loop, the hysteresis. Okay, basically, yes, there is a small amount of hysteresis in soil. You always have that in that kind of loading and unloading situation. But you will realize that when we are talking about recompression line, we usually regard the recompression line in classical soil mechanics. We usually regard the recompression line to be the same as the swelling line, to be the same. And so, in a sense, the recompression index is the same as the swelling index. It's the same as the swelling. Usually we don't have two different indices like a recompression. So that you are right, there is a small amount of hysteresis, and some material, not just soil, when you do the load and unload, actually has a small amount of hysteresis. But from the mechanician's viewpoint, all right, to keep the picture simple, we disregard this small amount of hysteresis. Now, there are people who produce model that take into this amount of this small amount. You know, this loop here, down and up. There's a small loop over here. There's a loop. There's a hysteresis loop. But if my understanding is correct, I mean, this is how you're just, it's basically treat them as one and the same line, right? The recompression line is usually regarded the same as the swelling line. And basically, when you measure either the recompression or the swell, and then you regard them to be the same. You know. So basically, the idea is that the two are so close that for the sake of simplicity, we will just treat them to be one and the same. And that is how a lot of people would usually regard it. You know. But there are some advanced model which feels the need to draw the difference. In fact, this line is not even linear. Coming back and going back up. It's not strictly linear. It's not strictly a straight line. There is a certain amount of non-linearity there. And some people actually describe, some models actually took great pains. I believe Andrew Whittle, MIT's model, that one of the MIT, I don't know, E1, E2, E3, and S1, or S2 or whatever, try to describe this particular thing. But for the purpose of our discussion here, I don't think we'll be able to go that far as to explore the differences between the unloading and the reloading line. We will just have to regard it as one and the same, you know. Yeah. You are working on the loop thing, right? Yeah. So if you have models which are very refined and you need to do it, then you have to do it. But for the purpose of this discussion, I will not highlight the difference. I'll just simply say we do the classical soil mechanics style. We just regard it to be the same, one and the same. You know. Okay. And in fact, you probably noticed that it is actually non-linear. The whole thing is actually non-linear as well.